Please welcome Principal Investigator and Director for the Blue Waters Leadership Computing Project at the National Center for Supercomputing Applications, Bill Kramer.
So thank you all for being here. It's my honor to introduce our first speaker, Benjamin Treynor Sloss from Google, who joined Google in 2003 and leads their system reliability team. He led the development of the operations of Google's network, data centers, and production software infrastructure for their operations for their internal and user-facing services. He invented the role and the term site reliability engineering as a distinct discipline and officially creates, supports, and monitors and improves the availability and performance of large software systems and services. In 2025, Ben was promoted to the role of Chief Programs Officer at Google, leading a multi-year Google-wide efforts to include the data center efficiencies, AI diffusion, infrastructure capital structures, and long-term capacity and supply. He started his career as a software engineer at Oracle at the age of 17 and has worked for several other industry notable software companies. So we're very fortunate to have him here. He's here specifically for today, and I'd like to welcome him to the stage and turn the session over to him. We'll talk for about 40 minutes with some questions hopefully at the end. Ben, thank you very much.
Thank you, Bill. Alrighty, so I'm here today to talk about deploying machine learning at a gigawatt scale and some of the things that we've learned along the way and are still learning along the way about what it takes to do that. So let's see, we've got our slide up. I think it's useful as a preamble to note, you hear a lot these days about gigawatt scale or 10 gigawatt scale. And if you were to read the press and sort of pay attention to the news, it would seem like this is a thing that just happens a lot, right? That, you know, a gigawatt scale data center full of machine learning is kind of about as common as Starbucks because everyone's talking about things that are going on beyond there. It's useful to understand just as sort of a preamble that there is an order of magnitude more functioning fusion nuclear reactors in the world than there are gigawatt scale machine learning deployments, or actually gigawatt scale computing campuses in general. And that backdrop of the amount you hear about it versus the reality, how far we are pretty far apart, is a lot of what underpins the motivation for this conversation. So with that, sort of let me dive right in. So first thing to realize, right? Deploying 100 megawatts was a big deal just a few years ago, right? I have been at Google now for a bit over 22 years, and 100 megawatts at the time when I started was unthinkably large. Now, it's not only not large, it's actually routine, right? A number of the hyperscalers sort of stamp out buildings this size, often several a quarter. And all of the large AI labs at this point are running at multiples of this scale, and we'll call this GA, right? Okay. Gigawatt scale, novel, right? There is no way right now to sort of talk about what a gigawatt scale campus is without sort of talking about all of the problems that go into planning for it, building it, deploying it, et cetera. And so I'm going to get into all of these as we go through the presentation. But one of my favorite little lemmas here is something that Jeff Dean came up with at Google a while back, which is every 10x increase in scale, you kind of have to redo everything. And unfortunately, Jeff is once again correct. As we are going from deploying things at the 100 megawatt scale to deploying things at the gigawatt scale, it is turning out that we kind of have to redo all of our different major pieces from deployment and planning to operations. And in particular then, I want to talk about 5 pieces that are part of the gigawatt scale journey that merit particular attention, whether you're simply interested in this or whether this is actually something that you have the misfortune of being pulled into being responsible for. But the areas that I want to talk about are, first of all, planning and construction, then the actual act of deploying and commissioning servers at this scale, the network that you'll use to connect this gigawatt of machine learning that you now are fortunate enough to have, the lifecycle management, right? What do you do with a gigawatt worth of machine learning servers over the course of their roughly 6-year useful economic lifespan? And then finally, my personal favorite topic, reliability, and how do you manage the reliability of not a server or a rack of servers or even a data center of servers, but multiple campuses of servers, and still get the thing you want out of them, which is either very efficient large-scale training or very high-performance inference, or most likely some combination of the two. So with that, we're going to talk about, as I say, the planning and construction. In particular, with planning and construction, one of the big issues that you have to worry about is how fast can you build versus how fast is the technology evolving. And also the problem that much as we would like construction to be a very sort of routine, normal, predictable activity, I don't know anybody here who's been involved in residential construction will probably be right there with me on this. It turns out that construction is not a predictable activity. It doesn't happen on a schedule and you sort of stamp one out and it's 17 months and you stamp out the second one, it's exactly 17 months. It doesn't work that way at all. And so you have to deal with scheduling uncertainty during construction, which would be a problem all by itself because it's a lot of billions of dollars. But when you start saying I have coordinated construction for a bunch of different campuses, it's become really quite exciting. The deployment becomes interesting, right? A classic data center deployment is very, very different from a large-scale machine learning deployment, and that's everything from supply chain to material flows to logistics to material handling to things like security and staffing. The network planning is also interesting because, of course, network, especially WAN network, has a long lead time. So you need to decide what network you're going to build, or on the same time you're deciding what buildings you're going to build. But the actual technology of using machine learning advances extremely quickly, and so you change your mind a bunch of times, and you have to think about what kind of network you build and how big you want it to be and how it connects the different nodes together. So we'll talk about that. There is this issue of server lifecycle, and in particular, the differences between using servers for training and using them for inference and using them for fine-tuning, et cetera, and then the fact, as I said, that the technology is advancing extremely quickly, and so you have to worry about the lifespan of these servers and the different uses that they'll get put to. And then reliability, both reliability as it pertains to an individual server, as it pertains to a rack of servers, as it pertains to a data center, and finally, as it pertains to a set of data centers. All right, so with that, let's dive right in. So I want to talk about planning and construction first. Fun topic if you've ever been involved in actually planning or building data centers. They are their own beast. But the traditional model here for a 100 megawatt data center, something small, right, is you build the data center, you gradually fill it up with servers as demand shows up and people either buy services or the use of the services that they were running there expands. Apparently, there's a business model involved in this that is where the money comes from, I'm told. We didn't get involved with that so much in the building side. And life is good, right? And when you think about building a data center like this, there's lead time, but there's also throughput. I think lead time is really a planning problem, whether it takes you 9 months to build a data center or 18 months to build a data center. That's just a question of how far in advance did you have to predict the demand and how much buffer do you carry. But throughput is a really interesting question. And what we see is typically the most you can build at a campus is 100 megawatts to maybe 200 megawatts a quarter, right? And that's more a problem of there aren't enough people, there's not enough skilled trades, it's very hard to get all of the materials in, it's very hard to get construction equipment in. And so whether whether it's 100 megawatts or 200 megawatts, if you're sort of planning for a campus and you want to build one of these things for 100 megawatts, you can, within a quarter or so, have your building up and running, assuming you started with enough lead time. 18 months ago. And so life is good. You build your campus, it has its 100 megawatt data center, and quite sufficient. All right, however, if you want to build a gigawatt, right, this is now a huge problem because you still have the same throughput limit that I was talking about. You can build, depending on the site, depending on how many people there are around, et cetera, depending on environmental conditions, you can build 100 megawatts to maybe 200 megawatts a quarter at this site. And so what that means is that if you want to build a gigawatt, well, you're going to be building there for a year and a half, right? Maybe a little more. And this whole problem then is, well, okay, but what do you do in the meantime, right? Because a year and a half building a data center campus, right, is actually longer than the generation cycle of the machine learning servers that you want to put into them. In fact, it can be twice as long. And so now you have this issue of explaining to your finance team, well, I'd like to spend, $12 billion, right, to build a gigawatt-scale data center campus, but it's going to sit empty kind of for a year while we're building it. And then when it's all done, we're going to fill it, right? It turns out they're really uninterested in this conversation. And they more or less come back and say, well, that sounds interesting, Ben, but why don't you come up with a different plan that doesn't have us having $10 billion sitting around doing nothing for a year, because people don't like that. Turns out, in addition to the finance problem, there's also a more practical problem, which is that if you've built, let's say you're halfway through and you've built 500 megawatts of data center and it's sitting there empty, someone else will find a use for it, right, while it's sitting there, while you're trying to hold it. And so we have a saying in the data center team, which is that nature abhors a vacuum, right? But what actually happens if you build a data center and you're trying to sort of buffer empty data center space, someone else will come along with a really compelling business case and say, no, we should put these other servers in there, or we should put the next generation in there, or whatever. So you basically can't do this. And that is essentially a deal killer, right? So you can't build a gigawatt-scale campus for machine learning on its own. You have to do something different. So what you do, sort of natural once we've explained the problem this way, is you have to go parallel, right? So if you want a gigawatt scale for a given generation of machine learning, you actually need to build several campuses, and you do them in parallel. And I used this screen grab from one of my favorite hyperscalers, but they all would kind of look the same. You build a bunch of campuses that are in kind of the same general geographic area, and you choose them so that you can get enough throughput at each campus to be able to get to that gigawatt limit that you're looking for within the time frame that your server deployment and server supply chain are actually going to allow you to have a gigawatt worth of servers. That time frame can be 3 to 6 months, depending on how much allocation or where you're getting your servers from, but it's not going to be more than 6 months typically. And if you're getting 200 megawatts per campus, that kind of means you need 3 or 4 campuses. If you're getting 100 megawatts throughput per campus, right, you might need 5 or 6 campuses. We'll get in a second to the trade-offs between those. But one way or another, you're going to end up building several data center campuses at once in order to be able to get to a gigawatt scale for a single generation of machine learning. And really, this breaks down eventually to the throughput pace that you've got, the number of campuses that you've got, and the rate at which the machine learning servers are evolving dictates the number of campuses that you've got. This was more challenging when NVIDIA, for example, had 4 generations of servers coming out in a single year. You could imagine what that does to your parallelism. Now that we seem to be settling down to something more like 1 generation per year, it's a more tractable problem, but it still requires going very, very parallel. All right, so we're going to build our gigawatt. We're going to build it in, let's just pick 5 campuses. It's a nice round number. And we'll have it up and running within 1 6-month period. Life is good, right? Well, not really, not yet. So here's the next problem. Traditionally, you build a 100 megawatt data center, and like I said, you fill it sort of as demand shows up. So on the near side, you might fill it up over the course of 12 months. If it were a more traditional service that maybe is growing, 20% or 30% a year, some boring rate like we used to see, maybe it gets filled up over a couple of years. So let's do the math. You have a 100 megawatt data center. You want to fill it, and we'll pick the upper end. Well, we want to fill it in 1 year, the upper end of this. A rack is 15 kilowatts, so a 100 megawatt data center has about 6,700 racks. There's 250 working days in a year. So you need to average 27 racks a day going into this data center, day in, day out, every single working day of the year, in order to get it filled. Now, world never works like that, right? There's material delays, there's shipping delays, there's demand ebbs and flows, there's generation changes. So we use a 2-to-1 peak to average to say, well, what's the throughput that I need to get at this data center? And you do that and you say, okay, fine, if it's 27 racks a day on average for 250 days, then the peak that I need to accommodate is 50 racks per day moving into a data center. And this is, fully populated rack full of servers. This is a 4,000-pound thing that, we talk about it like moving a Volkswagen sideways, right? You have to get it into the loading dock, you have to get it through your security, you have to make it safe for all of the people who work on it, et cetera, et cetera. It comes in packing materials, and you have to take the packing materials off, and so now you have, Volkswagen-sized packing material waste coming out of the data center at the same time that the servers are rolling in. This is a pretty big deal, but it is tractable if you plan the data center for it. You can get 50 racks into a data center in a day with sufficient effort and labor and a bit of planning. A good, if you want to sort of visualize what this is like, if you have a 10-hour working day, you have 12 minutes to get a rack, from the loading dock, unbundled through each stage, basically, of the process. And you can pipeline it, but it's still 12 minutes per rack is a very fast rate. But as I said, this is the traditional version. So let's look at what it looks like when you're talking about a gigawatt scale. Sadly, not entirely an exaggeration, even though, of course, this is a computer-generated slide. So I tried to make it a little bit easier for us here by saying we're going to do all of the work, right, in a 200 megawatt data center, and we're going to say, because these are all machine learning racks, they're not pulling 15 kilowatts a rack anymore, they're pulling 30 kilowatts a rack. That's on average. That's actually about right, because although some machine learning racks pull more than that, you also have all of the associated compute and storage and network racks and everything else that goes with them, so you can't use the peak, you got to use the average. But still, they're machine learning, so they pull more power, so it's 30 kilowatts a rack. It's a 200 megawatt data center, so we make the data center twice as big. That gives us that 5 campus number that I referred to earlier. And you have to get them all done in 2 months now, because we're trying to populate this whole set of campuses in just the 3 to 6 months that I talked about. So you've got 2 months, 42 working days, gives you 160 racks a day average, right? And again, 2-to-1 peak, because it turns out machine learning machines, just like everything else, have ebbs and flows of logistics and so on. So you now have to do 320 racks per day. That's what your data center has to be able to take. So that's 1 rack every 2 minutes, and you have to do this in 5 different data centers all at the same time, right? Or you've missed your mark, and again, the finance team comes and finds you, except now it's not $10 billion that they're complaining about, because it's these machines, and the machines are, to use public numbers that I've seen, 4 times as expensive, right? So now they're like, you have $50 billion of capital sitting around not doing anything for us. What on earth is going on? And that's a really uncomfortable conversation that I prefer to avoid. But the thing is, in order to make this work, then you actually have to design the data center differently, right? You cannot get a rack off of a truck, through your loading dock, unpacked, through your security, down the aisle, rolled in, right? Like, you can't do those stages if you have a traditional data center design. They just don't have enough throughput, as it were. So you have to deal with a data center that has multiple points of entry, multiple security points, multiple directions for racks to get onto the floor, multiple egress paths for the waste, et cetera, et cetera. It also drives you to use a different staffing model. You sort of realize, well, I can't staff for 10 hours a day, 5 days a week, nonstop. I actually need to have 3 or 4 shifts of people, right? And so you see firms going to 24/7 staffing, it's totally worth it. And if you have to pay the people 3 times as much, it's still totally worth it because, again, $50 billion, right, is the denominator for all this material that's going in. But paying people 3 times as much does not solve the problem if you've built a data center sort of traditionally that doesn't have this kind of throughput flow for it. So this makes it fun, and it particularly makes it fun if someone maybe not in your team comes up with the bright idea of saying, well, let's use an existing data center and populate it with these things. And then you're trying to well, maybe we have to put a hole in the wall, right? Has been done. So this deployment problem actually turns out to be fairly severe, and it's one of the big things that you need to deal with when you're trying to do one of these large-scale deployments. I'll note, finally, for the record, I'm only talking about a gigawatt here, right? There are plenty of planned deployments that are larger than this, and so you can take all of these problems and multiply them further. All right. So let's talk network for a second. Another of my favorite topics. Traditional ML deployment, everything kind of lives in one building, right? 100 megawatts, it's cute, it's small, it fits in a single large building. And you put all your machine learning in there, you do data center level network to interconnect all of these machines, and you can kind of wire it up however you want because everything is inside the 4 walls of that data center. So you build your LAN, if you need more network bandwidth, you put extra switches in, maybe you do a tiered hierarchical network. Life is good, right? But with this gigawatt scale, again, none of that works, right? You have to interconnect the data centers to each other, and that means that instead of sort of doing on-demand or last-minute network deployment inside the data center, you now have to plan out a WAN network. And it should be noted, these are not small numbers when you start planning the WAN network, right? They start with petabit and not a single-digit petabit. So you actually have to get fiber routes. You have to use trenching machines like the one pictured here, but you actually have to plan this network out at least as far in advance as you're planning the data centers, because you're going to have to run a bunch of dark fiber between the different data centers that are participating. And one of the things you do is you run more dark fiber than you need, and then you make a later binding decision about how much of that fiber to light. The use of the network by machine learning is also, unfortunately, very unpredictable for those who follow this along. The network bandwidth between participating nodes in training for machine learning is very large, but actually also not known 12 months in advance. And it's not because the teams that are working on training like to mess with the teams that work on infrastructure. They're doing R&D. They literally don't know, right? And they'll come up with a new idea every few months for something that they could do differently. And they're like, this is fantastic. We can get a 13% improvement in recall or quality or training speed. And all we need to do is have 4 times the network bandwidth between the nodes, right? That's easy, right? And here you are. So this basic problem of you have to decide how much network to provision for when you're building out this campus about as far in advance as you're building the campus itself, but you really don't know how much network is going to be required to make the thing work optimally, creates a fairly serious problem. And it's not a $50 billion problem, but the network you put in will affect the ultimate performance that you get out of these things. So it's a fraction of $50 billion right there. Super simplified graph just to illustrate. There is actually a solution for this which will be guaranteed in some sense that everybody will be irritated with you, but they will roughly be irritated on both sides of the equation, which is really often the best you can do in infrastructure. And it's basically this, right? You need to spec the WAN bandwidth before you actually know what the usage is going to be. The WAN actually costs a significant amount of money, and in fact, it costs so much that you start to make the trade-off between how much WAN do I build and how much machine learning can I afford to buy. And this is actually the key, right? So what you can do, because you have this trade-off, is you can say, well, I know that the more WAN I build, the more performance I'm going to get out of the machine learning that I'm deploying, no matter what their bandwidth eventually is. I don't know how much more performance yet, because I don't really know what the peak of their demand is, but I know it'll be more. But I can now create a probability distribution, right? This much bandwidth leaving me that much money for servers. Here's my expected range of good put out of this combined system. and you can change the mix. You can have more network and fewer ML servers, or more ML servers and less, network bandwidth, and run the computation to tell you what's the total good put of this system under a range of possible network demand for training. And that is basically then a Monte Carlo problem, which you can run. And again, with this many $1 billion, I highly recommend that you do run it. It really turns out to be worth it. And then you just pick the point where your expected good put from the combined system is optimized with the amount of network that you're building. And like I said, and then you subsequently find out how much network they actually wanted, and they're either irritated at you for not having built enough, or they're irritated at you for having spent so much on the network that now there's less money for machines. But if roughly half the time they're irritated on each side, that means you've nailed it. And so I like to say the summary, this slide sort of illustrates it, but ultimately the ideal network WAN capacity is solved by running the news vendor analysis for the performance curve for good put that you get from a Monte Carlo simulation of the system. And that's a lot of words, but trust me, this is actually how it works out. And at this scale, it turns out to be very much worth running those equations. All right. So if that's network, let's talk server lifecycle. So we've spent all of this time and effort to build our 5-campus gigawatt-scale data center capable of being fully populated in 2 months if you run round-the-clock shifts and so on and so forth. And we've put all of the current generation of machine learning hardware into it, and everybody is happy for roughly 9 months. And then they come back and they say, well, this is great. I love this campus, but this isn't the new hotness anymore, right? This is last year's model of machine learning, and now I want the new machine learning that's just been announced, right? Whether you're an NVIDIA fan or a Google fan or an AMD fan, or you build your own chips, right? Roughly speaking, the teams that do frontier model training want the best and latest hardware because that's what all of their competitors are going to have, and they will sort of immediately want the new generation of server once it becomes available. They'll actually want it before it becomes available, but bear with me here. And so now you have this problem, which is that you've built a gigawatt of data center campus. You've filled it with what amounts to $50 billion worth of hardware, and now no one wants your campus anymore, or more precisely, they want another campus with new hardware in it. There's a further problem, which is that for training, you want all of your capacity concentrated in as few campuses as possible for the reason we just talked about, right? Fewer campuses means less network you need to build, which means more money for ML, blah, 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 blah. But they want it super concentrated, right? A few campuses relatively close together for lower latency and lower network cost. And as soon as you're not using it for training anymore, that's actually basically pessimal, right? You have the worst reliability because it's only in a few buildings. You have the worst latency because it's all in one place in the world, but your users are all over the world. And we can't change the speed of light, right? So what do you do? And this, by the way, will be true for 5 of the 6 years that machine learning capacity has a useful economic life. So for 5/6 of its time on Earth, people will not want it in the configuration that you originally deployed it in, and this turns out to be a bit of a thing. I would say this is an unsolved problem right now, but there are a few sort of obvious things that you can do. The first is you can simply plan the campus to be expandable, right? You've already laid the network in, so if you could just build more buildings in this campus every year or every year and a half, then you could reuse all your network and you could deal with the concentration, and at least you've solved half of your problem. You don't need to build, $5 billion worth of network a second time. But you still have the problem of all of that hardware still in one place, and you would really sort of prefer to have it everywhere. Another is you can plan to simply relocate some of that hardware out of the data center that you so painfully deployed it into just 12 months earlier and distribute it around to inference nodes elsewhere in the country or elsewhere in the world. And you could also, just say we're going to run more complicated machine learning problems on this particular set of capacity because those are slower by default, And so therefore, although there is a latency difference for most of the users in the world, they don't really notice because the 120 milliseconds that it takes to get to this capacity from most parts of the planet is swamped by the 5 seconds that it takes to actually run things. So for example, if you were going to run video generation, this would be a great place to run your video generation because it's going to take 10 seconds or 30 seconds to make the video anyway, and nobody's going to notice that it took 120 milliseconds to ship that video to you once it was done. But do plan ahead for this because this phenomena will crop up, and I kid you not, it crops up while you're in the middle of deploying the current generation often, as you sort of get the request, well, hang on, we've heard about the next generation that's coming. Where's it going to get put? All right, so good fun. Finally, let me talk about reliability, and this is an interesting topic. I've spent a lot of time on this over the course of my career, but it gets particularly interesting with machine learning. So here's the basic conundrum, right? Training requires large amounts of the same node type, all participating basically in a synchronous operation to do computation. And in that world, a single node failure breaks your computation. You then have to revert to some earlier point in time, pull in some redundant capacity, and restart the calculation. At the same time, what I just said a second ago is also the problem, right? To do frontline training, you want more and more nodes participating in this same training run. So you have this problem of, as the node numbers go up, right, with a constant failure rate for any given node, your failure rate goes up. But also, as the number of nodes go up, the cost of a node failure, a cost of a restart, also goes up because you basically have made the work of all of these nodes worthless for the, whatever time they spent since their last checkpoint. And so the key insight here is that the cost of node failure, or conversely, the value of node reliability, goes up quadratically. It goes up with the square of the size of the participating pool because both you have more failures and the cost is higher. There's a corollary, which is helpful, which is that for a given level of node availability and a given training pool size, there is an optimal frequency with which you should give yourself a checkpoint to restart to. And you can calculate that, and actually you should, because it will really determine how big you build these nodes. But there's also another corollary which is less fun, and people do not like this one. There's actually a maximum number of nodes that you can have for a given node reliability before adding an additional node actually decreases the throughput of the training cluster, right? That the cost of the additional failure from that node takes away more performance than the additional anyway. And for this reason, I think you'll see all of the hardware providers starting to really push on node reliability, whether you consider node an individual server or a pair of racks or whatever. It is a really almost impossible to circumvent gate on the maximum scale that you can do training at, and the only way to get around that gate is to basically make your nodes more reliable. And conversely, or similarly, you can calculate how big a cluster you can build once you know what the reliability is of a node. And investing in node reliability pays off very handsomely as the node scale gets large. So as I mentioned, what you should do in this situation is you should create yourself a good put model, right? Which says, here's the number of nodes, here's how much they cost, here's how much they individually contribute, here's the reliability that I've got. I can figure out what my maximum good put is, and I can figure out if there are places where I could invest money to improve reliability, how much is it worth to me to get a reliability improvement, because it actually makes the entire $50 billion setup produce more good put, and that even a 1% improvement for $50 billion, it turns out that's still a lot of money, and people pay a lot of attention to it, including your finance team. It's also worth noting that whoever it is that's using these training clusters, they don't actually care how many servers you've got in them. I mean, they talk about it, right? They talk about megawatts or server count, but what they actually care about is the good put of these clusters that they are getting from you. And so if you take the actions that maximize the good put they get, they will be very happy. And conversely, if you give them a ton of servers, but actually the thing restarts all the time and they can't get their training runs complete, they will be extremely unhappy. And so I highly encourage anyone building a large-scale cluster to do this solve. And I think what you'll find is it guides you to make node reliability and for that matter, node interconnect reliability much, much higher, because it lets you get much higher good put out of this very large capital investment. All right, so with that, I will tell you, when I was asked by the illustrious David Patterson to come and speak on this, I started with deploying a gigawatt. Like, how am I going to fill 45 minutes with that, right, for a large crowd? It's such a specialized topic. You all will have to be the judge, but I will tell you, by the time I got done to it, I'm like, oh my God, I've barely scratched the surface of this topic, and I'm going to run almost completely out of time, and I did want to leave a little time for Q&A. But I have really just scratched the surface of this here, and I encourage those of you who are going to end up being involved directly or indirectly in large-scale HPC to work through these problems, because they're not necessarily obvious if you're coming from a tenth this scale, but they have an enormous impact on the outcomes that you get for this very large capital investment, and they will pay off handsomely, right? Because again of the dollar figures involved. All right, so with that, I have timed it actually fairly well. I've got 10 minutes left, and usually I found the audience questions can be some of the most interesting parts of the presentation. So let me open this up, or if you have online ones, I will take those.
Well, first let's thank Benjamin for a great introduction. If you're going to ask a question here in the room, please go to the microphones, identify yourself and maybe where your site is, and then ask your question. We do have online questions, and I'll kind of alternate between the online ones if they come in. So.
Hi, Carl Ackerman from BNP Paribas. You spoke about the theoretical good put of a fixed number of training compute nodes or overall nodes. I'm wondering how that, what is the average number of nodes, whether it's per building or per campus? What's the rough approximation we should consider? And then how might that number change whether we use a different networking transport protocol such as InfiniBand versus Ethernet?
So I will say there isn't an average so far. Again, the actual number of gigawatt-scale campuses in the world is under 6, right? So like I said, the difference between what you read in the news, where, like I said, it seems like these things are like Starbucks, right? And the reality is this is very much a work in progress for everybody. There's lots of 100, 200 megawatt deployments. There's not. But to answer your question, I mean, the number of nodes per building is going to end up being a function of two things. Number one, size of the building. I mostly have not seen people building buildings that are more than 200 megawatts each. And part of that actually is network reach, right? The optics that you use for a data center network have about a 2-kilometer span, and it turns out by the time you're done running right, because the longest one can be 2 kilometers, right? So these buildings end up having a finite size, and so what you start to see are like some of the folks are building this kind of hub model where you have 4 buildings around a central hub that's actually the network hub that connects it over to the other hubs nearby, or at least that's what their plans look like. But I think 200 megawatts is probably a reasonable upper bound for what you're likely to see for a building. And then if you want to know how many servers go into there, well, you take 200 megawatts and you divide it by the power, the workload power rating of the generation of thing you're going to put in there. It is one of the reasons I think you're seeing a lot of the upcoming generations of high performance computing moving to these higher power profile. Although, important note, we talk about racks, and they talk about, well, it's going to be 200 kilowatts a rack. Not really, right? What they're calling a rack is now a 4-rack-wide construct that's nearly, anyway. A rack, it turns out, is a fairly malleable term. So we talk about, power per square inch is a nice metric. But certainly if you can make the power density higher, then you can pack more servers inside of the span reachable by your favorite network technology. I don't know that it is so much a function of whether you're using Ethernet or InfiniBand or et cetera, but I do know that, again, the reliability of the interconnect system is absolutely critical for the reasons we just talked about, right? You lose so much good put when you start having frequent node failures, and as the number of nodes scale up, you need to have a very, very high node reliability, or your system basically spends all of its time restarting.
All right, can we go to the middle?
Detlef Hohl from Shell. How much overall do digital twins play in the design, construction phase, operation phase of your data centers? You spoke about simulation and modeling. You spoke about sampling, distribution functions. I assume it plays a big role? Or maybe not?
So the ugly reality. I would say digital twins, not so much, right? I don't know of anybody who's doing a full-blown digital simulation of this. Digital modeling of the key systems, 100%, right? So you are absolutely doing digital modeling of everything from CFD for your water and air flows on these much, much higher density servers, to modeling of the systems for networks, to modeling of good put for servers and collection of servers. All of those are really, really critical. But I don't know anybody, and they may be, and I just don't know about it, but I know a lot of people in this industry. Everyone is doing it right now sort of a piece at a time, rather than trying to construct a full simulation. I can't actually think of a time when we've run into a problem that would have only been exposed through a full-blown simulation, right? A lot of the modeling really is separable, if you will, into layers: the physical layer, the logical layer, the network layer, the server layer, et cetera. But it's a great question.
So I'll take an online question that came in. And what role does data center reliability play in overall reliability?
Great question. Interestingly, not much. And which is maybe slightly counterintuitive, but remember, it's the node count problem, right? So suppose you have a data center that is only, right, 2.5 nines available. How much downtime does that data center contribute to your 5 data center pool? The answer is actually not much, right? Because it fails for a very large number of nodes, but there's a very small end count. Now, if you had 1,000 data centers, that would be, a complete train wreck. But it turns out, especially for training, you can get away with fairly unreliable data centers, so long as you have very reliable hardware in the data centers. And again, this all, if you run a good put model, it's sort of, some of these surprising conclusions fall out, but it's an excellent question.
Okay, thank you. Why don't we go to the right side, or at least my right side, for the next question.
Hi, this is Pradeep from KLA. Incredible insights into Gigawatt. I begin to appreciate the complexity of putting it. But the question I had is a little bit more looking back, where you said that the frontier model developers obviously want to move to the latest and greatest generation. What happens to the older data centers? As somebody in Google who still stood up data centers for TPU v1 and all the way, are those still getting used? What kind of workloads are they running? Or are they just gathering dust now?
Yeah. So the good news is, in today's scarcity world, there is no dust to be gathered, right? The street finds its own use for things. So what we're actually finding is even 6- and 7-year-old ML equipment is still running close to 100% duty cycle. And the reason more or less is there's lots of things that you can run on them that they're still perfectly adequate for, and they're still better than not having capacity. But to sort of excite your imagination, right? We know that when you build a model, that model often is produced in several different sizes, right? Different computational costs to run, different memory requirement to run, et cetera, et cetera. Okay, great. So you can run the smaller versions of the models. Google calls them flash models, for example, right? You can run those on very old hardware. And sure, maybe it takes 4 times as long to run inference as it would on the frontline hardware, but it doesn't matter, right? It's going to run in tens or maybe hundreds of milliseconds, so you still get an answer, and you still have all that capacity, and now you've offloaded that workload from, yeah, you see where this is going. So it is surprisingly turning out that even though the pace of advance of computing power for ML is staggering, you're actually getting a lot of very productive use out of fairly old hardware. And so, yeah, we don't, there's nothing sitting idle right now, including, you know, the old generations.
It's good to know. Thank you.
Thank you.
Maybe time for 2 more questions.
Go to my left, and we have about 2 minutes left.
Okay, so first, fascinating. Thank you very much. I'd love to see the next 40 minutes. But looking in your crystal ball, you said every step of 10 is a complete reinvention, but you know, you're looking asymptotically at limitations on reliability. There's only so many data centers you can build in parallel. There's only so much fiber you can bury. How far can this go? 10, 100, a terawatt? Like, where does this end?
I always think about Bill Gates when somebody asks me a question like this. And I know that, you know, 640 kilobytes is just not going to be enough. I don't know where it ends. Let me be quite clear. I know what the next generation is likely to look like, and that it's not stopping, which is interesting. So very clearly, we're headed in the direction of densification for the racks, and densification of the racks allows you to get more, I mean, essentially more compute capacity within that LAN limit that I talked about earlier. And LAN limit is nice because then you can do things like, well, if reliability is a problem, let me just double everything up, right? It's not that expensive. And the impact on good put is so profound, right, that it's worth doing. I think, you know, the limit is likely to be defined by returning or decreasing returns on scale from the model outputs that we're getting from this, right, rather than by technical limits. And I say this only because, you know, I mean, if you remember Moore's law, right, 40 years ago, if you said, oh, this law is interesting, I wonder when it ends, right? If somebody told you, well, it ends 30 years from now, you'd never believe them. But where there's enough economic push or incentive, people keep finding solutions for things. I mean, I remember when, you know, whatever it was, 6 nanometer was the limit, right? And here we are. So I would say, to answer that question, look at decreasing improvements from adding scale, and that will be your practical limit. We can clearly go 10x from where we are right now.
Thank you.
With that, I am fresh out of time.
Yes, we are. So we're going to end this session, and I want to thank Ben for his very clear and interesting conversation. He's taught me that I shouldn't worry about my home remodeling project because it's taking so long. I should be doing 4 or 5 of them. So yeah. So, but thank you very much, Ben, and thank you for coming all this way.
Thank you all for having me.
Our next speaker is April Novak. She is an assistant professor of nuclear plasma radiological engineering department at the University of Illinois Urbana-Champaign. She leads research for fusion and fission systems using large-scale multiphysics and multi-scale simulation codes, including developing GPU-accelerated multiphysics tools that won the R&D 100 award. She has an appointment also at Argonne National Laboratory, where she was a fellow at Argonne's Computational Sciences Division, and she holds a PhD in nuclear engineering from the University of California, Berkeley. So, April?
So much. Excellent, thank you. Wow, it is wonderful to be here. Thank you, Bill, for the introduction. Thank you all for taking time to be with me today. I'm really excited to share with you what I see as a very complementary technology, how nuclear energy intersects with large-scale computing. So, as already said, my name is April Novak. I'm an assistant professor at the Nuclear, Plasma, and Radiological Engineering Department at the University of Illinois Urbana-Champaign, in case you didn't catch the long name the first time. I work with a large team of scientists and engineers across national labs and universities around the world in the development of the next generation of simulation tools for nuclear engineering, particularly ones that can leverage and take advantage of HPC to help us design better reactors and power this growth in data centers that we just heard about. So I have to begin by acknowledging this group of people, my colleagues and their teams, but I do think it would be more accurate if all of the names here were in alphabetical order so that mine moves somewhere in the middle of this wonderful group of people. And I'll be showcasing a lot of the work from this team today. So the thesis of my talk is that HPC is central to nuclear technology development in the modern era. HPC allows us to design better systems that can meet this growing energy demand. But I also see a duality here in that nuclear can be this clean power, this carbon-free energy to fuel this growth in data center demand. Nuclear energy has long been the United States' leading source of clean energy, and every revolution in technology requires massive amounts of energy. So this talk is going to be organized around these two ideas, not necessarily spending an equal amount of time in each, but I'll start with a discussion and overview of Department of Energy R&D programs related to modeling and simulation for nuclear. My background is primarily on the engineering and application side of things, so I'm going to talk a lot about prototypic use cases of how HPC is used for nuclear applications. I'll talk a lot about work from the Department of Energy Nuclear Energy Advanced Modeling and Simulation, or NEAMS program. But I'll also showcase work of my colleagues from the Department of Energy Exascale Computing Project, the EXA SMR team, and talk to you a little bit about GPU porting of nuclear engineering codes that form a lot of the analyses that I'll show you today. So I think the best place to start is with a reminder of how we design things. And of course, this is not a foreign topic for SC, but design hopefully is an iterative process where you begin by first defining a problem you hope to solve, whether it's designing aircraft or a nuclear reactor or the next supercomputer. You then collect data with a physical experiment or a numerical experiment to help you develop a solution to that problem. Maybe you can then refine the parameter space, or you can better understand constraints, physical or economic, on your concept becoming viable. And you do this in a loop, hopefully getting closer and closer to pushing your technology to something that can be commercialized, or even to a limit technological for that concept. So what does this look like for nuclear energy? If I try and categorize fission reactors into major groups, we usually talk about them in terms of what fluid we use as the coolant, whether it's water or liquid sodium or a molten salt, because that choice implies a lot of other downstream choices in the materials you use in the neutron energy spectrum. So high-level categorization of reactors can be made by the coolant. So if I look around the world, every reactor which has ever been built, and I look at the cumulative operating experience of those concepts by year, I see that we are dominated by water-cooled technology. Our current fleet is heavily water-cooled. Why is this interesting? I want to show you on a log-log plot, though, because there are some lines down there that are quite hard to see. So it's better if I show it on log-log so we can start to see them. But a lot of the early prototyping and design of nuclear reactors occurred in the 1960s. We built a lot of our first concepts then, and it was a quite diverse time for nuclear. We weren't exactly sure what would become the main commercial concept. But due to a lot of investment from the US Navy, it became a water concept around the world. Now, this is relevant today because a lot of the startups and new ventures which are designing nuclear concepts are not water-cooled. We're operating in this very data-scarce space where maybe the most recent reactor was built 50 years ago. Or maybe not at all. There are some concepts with 0 operating years of experience that we're trying to build the first time. So if you were in this situation, how would we do it differently than we historically had? And HPC has a really big role to play in that question. Again, in the US, some major DOE programs, the majority are using non-water coolants and are in this space down here. And we've had prototypes over time, but again, most of them are from decades ago. And a lot of this knowledge has been lost. Fusion is a similar story, although starting from a different starting point, of course. I like to say the first fission reactor was literally a pile of bricks. It's a different technological challenge to do fusion. But we've had a variety of science experiments over the last 7, 8 decades that are progressively getting closer to this point of viability. So today, HPC can play a really important role in nuclear design because the integrated conditions in a fusion reactor or a fission reactor can only be found in those systems. They can't be replicated fully independently without all the physics combined together. We're talking about very high heat fluxes, high temperatures, strong radiation fields which damage materials and really constrain some of the choices we make about the construction and composition. In fusion, we have plasma material interactions and very strong magnetic fields which also add a complexity here. Building a physical experiment for nuclear is one of the toughest things you can try and do. This can be very expensive and a very slow process. And so at some point, designing things by physical iteration, by hands-on stuff, testing, becomes too expensive and too slow for our ambitions. And so this is where I see HPC playing a really important role, because we don't have infinite time and resources to deliver this next generation of nuclear technology. So HPC allows us to make our experiments highly targeted by understanding what are the most important uncertainties we need to reduce, by making sure our technology is as mature as it can be before sending it to the most expensive stage of testing, and to making sure that the experiments we do choose to run show us exactly what we hope that they show us. So in the United States, there's been a lot of programs geared towards developing simulation tools for nuclear energy. And this plot here shows, as a function of year, the launch date of some of those larger programs. As a function of, the black line is the approximate size of a US National Laboratory supercomputer. So these supercomputers really allow us to not only discover fundamental physics relevant to nuclear, but to engineer systems and get them closer to commercial viability. Some typical use cases include designing experiments, deciding where to put sensors. You don't want to run an experiment and wish you had collected more data, but sometimes sensors are very expensive for nuclear applications, or they can only be placed in certain locations. Design optimization is a really big one for us, selecting the materials, the operating conditions, the control systems to get the most out of our technology. A lot of nuclear involves safety analysis. It's always at the forefront of our mind. And so being able to justify to our regulator that our reactor is safe for scenarios we may never test, like failures and severe accidents. And of course, when you operate a nuclear plant, there are recurring analyses you do all the time. These may not necessarily involve HPC, but concurrent refueling, power upgrades, lifetime extension are all things that will continue to be used even once the plant exists. So when we think about high fidelity, we talk about doing these types of analyses with more precise physics models, which allow us to reduce model uncertainty, gaining more out of our system if we can push it harder, informing constitutive models, and allowing us to explore full system interactions. That's not to say that this is easy. Nuclear reactors are some of the most extreme environments that we can create on Earth. There's a huge range of scales in both length and time. Turbulent scales, kinetic scales for neutron transport, all the way to radioactive waste systems in the environment. This can range quite far in extent. We work a lot with multi-physics simulation because we have concurrent interactions between fluid flow and heat transfer, neutron transport, and material science. And the techniques to solve those equations are usually very different. Some may run on GPU, some may still only run on CPU, and they may use very different programming and parallelism models. But you want them to work effectively together. Historically, we've built nuclear reactors where we can kind of isolate a unit cell from them and look at the most severe behavior in a small part of a reactor. But some of these new concepts we're looking at don't fit that mold. For example, pebble bed reactors are a really good example of this. Here are some simulations that our team has done over time, scaling to larger and larger systems. There's not a repeatable unit in here. To understand this, you really have to look at the full system. And we have a very robust regulatory landscape when it comes to nuclear. That adds additional requirements to our simulations. I'll touch on that towards the end of the talk, because it's important to remind us that performance is not everything for us. So the software I'm going to talk about that we develop in my team is called Cardinal. I'll just briefly introduce it. It combines a lot of decades of investment in nuclear engineering tools to tackle multi-physics and multi-scale simulation. We build on top of the Moose framework, which is a C++ finite element, finite volume framework, which allows you to build with classes quite complex multi-physics simulations. Some people use MOOS to build their own fully fledged nuclear fuel performance solvers. Others use this more as a data transfer framework to pass data between existing tools. We use it in that sense to combine two exascale codes, shown on the right and on the left. OpenMC is a Monte Carlo radiation transport solver, which was invested in through the Exascale Computing Project as part of the EXA SMR team. And on the right, NECRS is a spectral element turbulent incompressible flow solver, also part of the EXA SMR team. We combine these two ECP codes together to look at multi-physics interactions in nuclear systems. So I'm going to talk briefly about those GPU porting efforts, starting with OpenMC and the Monte Carlo method. And I want to spend some time telling you what I think is interesting about our PDEs that we solve. So with Monte Carlo radiation transport, we are solving the linear Boltzmann equation, shown here. It's highly dimensional, 7-dimensional phase space. Historically, we have solved this with a variety of operator splitting methods for the neutron energy and the neutron direction of flight. Our physical data for nuclear engineering is very complicated. We call our physical data cross-sections. They're the coefficients in this equation. They represent probabilities of interaction of neutrons with nuclei. A typical cross-section is shown in the top right there. Very resistant to curve fits. Typically 10,000 points to represent the behavior as a function of neutron energy. So with the Monte Carlo method, what is really attractive is that we don't need to discretize that. And we don't need to discretize an angle, removing two of the major losses of accuracy when we solve this equation. It is a Monte Carlo method, which means it's a stochastic solution to this equation. So we have probability distribution functions for all of the interactions that a neutron undergoes. So the distance to the next collision, the type of collision, and the collision physics, like scattering laws. Something unique for us as well is that when neutrons interact with matter, they transmute that material and change its composition. So chemists, they have a periodic table of the elements. Nuclear engineers, we have a chart of the nuclides with every isotope of every element, because sometimes there's quite different behavior by isotope. So over time, when you put a material in a reactor, you're creating more and more identities of material, which requires a lot of memory to store all of this data, and means that one of the most difficult parts of running Monte Carlo at scale is that very stochastic memory access, very high cache miss rates for these types of tools. So OpenMC is an open source Monte Carlo transport code. It was ported to GPU using the OpenMP target offload model and has shown excellent performance on all of the major GPU vendors. This really came out from a very close and intentional collaboration with the compiler teams, as well as the Oak Ridge National Lab Shift team, also working on GPU Monte Carlo. Some important algorithmic changes made this possible. On CPU, the typical parallelism strategy is called history-based parallelism, which means that you run one neutron at a time. Those black jagged lines show the random walk per thread. So the parallelism is over particles on each thread, so that each thread is probably not doing the same type of task as another thread. On GPU, what works a lot better is a different technique called event-based parallelism, which means that we form these queues of the next event to execute. So we deconstruct all of the possible sequences in a Monte Carlo code down to 7 or 8 different events, like ray tracing, crossing material boundary, sampling a cross-section, and form these queues of particles waiting to execute that, and then execute them all with threading. So this really improves the memory locality, a lot of speed up on GPU, about 6x from just this. We also do on-device sorting of the particles based on the energy and material that they are in. This is, again, attempting to improve the memory locality, and it is very attractive for GPU to get that higher throughput. Some CPU-specific optimizations we found were able to be removed, such as caching of some information. With the sorting, we're able to just read that data from memory more efficiently. So by removing some cached information, we free up memory, allowing more particles to be in flight at a given time. So this tool through EXA SMR was tested on a specific challenge problem, as shown there in the bottom left. That is a small modular reactor. It's representative of the concept that NuScale is trying to commercialize, a light water reactor. And what makes it notable is that it uses 300 different nuclides from the chart of the nuclides. It's a depletion simulation with 200,000 unique fuel regions. So maybe one of the largest calculations with Monte Carlo done to date. And so those are the performance numbers on the top for weak scaling for that problem. So becoming the first Monte Carlo code to do 1 billion particles per second, which is quite exciting, I think. Okay, quickly about the other tool, NECRS. This is the other part of the EXA SMR team. This is a CFD code using the spectral element method. So incompressible Navier-Stokes. This tool builds on programs such as SEED and is built upon the libparanormal library for the ACA portability layer, as well as historic efforts with the NEC 5000 CFD code. It's a high order method. So that means a typical element has 8 cubed degrees of freedom. This is very attractive for turbulent simulations because it is minimally dissipative and dispersive, which means that when we have 1 million or 2 million time steps for calculating turbulent statistics, this method performs very well. Time advancement is done by sub-stepping for advection, pressure, and viscous, the parts of the solves, so that we use different kernels for each that best behave for that characteristic of the problem. So NECRS is written in C++, uses ACA for portability, and just-in-time compilation to get the vendor-specific code when we run on GPU. The first full-core CFD calculation for a pebble bed reactor was accomplished with this code in 2021. Those are some beautiful images here that I like to show. This is run on all of Summit at the time, so 51 billion degrees of freedom in 6 hours of wall time for a full flow-through calculation. That is representative of commercial concepts for pebble bed reactors, which are a type of new reactor that we're pursuing in the United States. Okay, so these are some of the tools that have been invested in through ECP and form the foundation of a lot of current HPC research for nuclear engineering. So I want to change gears a little bit and show you some prototypic use cases for how HPC is used for nuclear technology development. And I've tried to sort these into 3 main categories of where I commonly see HPC used. The first category comes with the ambition to reduce model uncertainty. We didn't have supercomputers when we designed our first nuclear reactors, of course, but when we use low-fidelity tools or things that run fast, we have a lot of uncertainty in those answers. So we way over-provision our safety systems. We pad everything so we are sure we have a lot of margin to anything failing. That's not necessarily the most economical proposition. So HPC plays a role here in ensuring that those fast-running methods indeed are conservative, especially when we look at new reactors which have never been built before. We might not have data. We want to confirm that. And then if they are conservative, can we push our system to be closer to failure and therefore recapture some of that design margin as economics? If we can push closer to the maximum temperature, we can raise power, and therefore we can get more power output of our reactor, still safely, of course. So I'll show you 2 examples along these lines. The first example I'll show you is for what are called TRISO fuels. These are a type of particle fuel form. It's a relatively new type of nuclear fuel. Not very many reactors around the world use this. But the idea is that we have tiny microspheres of uranium, and we coat them in some protective layers, and then compress them into cylindrical tubes. And those get placed into a reactor in addition with the cooling systems and the structures around them. Why is this interesting? These types of spheres, some of those layers act as thermal insulation. So you can kind of think of a reactor as being a whole bunch of little point sources of heat. That's important to capture in terms of the effect that it has on the neutron transport. And it's difficult to do that because these particles are randomly positioned inside of the core. So we don't know their positions. We can sample them to get a realization of them. But we want to understand how does that locality of the heat source change our behavior of the neutron transport. It's also important to get right in terms of fission product transport, mass transport. When fission happens, we split the atom and we create 2 radioactive fission products. Those are mass species that like to diffuse, potentially getting across these protective layers and into the coolant, where they become a radioactive source term that influences how you do maintenance and how you design shielding. So we look at simulations like this, where we have these microscale models of fuel compacts distributed throughout a reactor. And we look to see how does the fission product differ between doing a high fidelity model like this as opposed to two different low fidelity methods. And so just looking, for instance, at a single isotope, silver 110, you can see that the high fidelity prediction, it is indeed bounded by a conservative and under-conservative method. But if we're able to use this compared to the under-conservative prediction, we can push our method, our reactor, higher temperatures and get more out of it without releasing more silver. Another use case I'll show you has to do with lifetime extensions of nuclear reactors. There's a rule of thumb: every day that you can continue operating a gigawatt-scale reactor, that utility makes $1 million. So modeling and simulation plays a big role in deciding how far can I push the lifetime. One of the most important components in a nuclear reactor is the reactor pressure vessel. There's a photo of one there up on the top left. This component is in the plant for the lifetime of the plant. If that fails, the plant shuts down. If there's a loss of cooling in a nuclear power plant, like a pump fails somewhere in the primary loop, there will be a lot of backup systems to insert more water into the reactor. This is called cold water injection. And when that happens, this reactor vessel, which is hot, can be thermally shocked. And then any kind of initial defects in the reactor vessel may grow and crack. So this is a type of safety analysis that we do when we look at lifetime extension of nuclear reactors. So using the tools mentioned before, for instance, we may run a CFD calculation of that cold water injection. This isn't necessarily the biggest CFD calculation done, but what makes it notable is it's a very long time integration that we're doing here, because the physical transient evolves on the scale of hours. And so we look at a cold plume of water coming in and the buoyancy and mixing that affects, and then the temperature experienced by the reactor vessel and the thermal strains that result. So providing that information to a probabilistic fracture mechanics model, we can look at the most likely locations of failure, of cracks, and to make sure that that is well below our safety requirements. What's interesting about high fidelity, those two images in the middle, is that we can see the location where cracks are likely around that belt line weld, compared to losing all of that spatial information if we use coarse methods, low fidelity methods, where we might just assume everything is at the lowest temperature, the most severe case. So calculations like this help us push nuclear to longer lives. Okay, my second category for how HPC is used for nuclear is perhaps one of the most common. A lot of the nuclear industry has a set of tools that they've invested in to design reactors. Those tools may not be solving the first principles physics. There are constitutive models or closure models in there. For example, friction factors or heat transfer coefficients if we're talking about fluids. High fidelity CFD can be used to generate new constitutive models that are tailored to your system and therefore have reduced uncertainty associated with them. Many of these constitutive models that we do have today come from very old experiments, which are maybe not perfectly aligned with the system that you're designing today. So to show just one example, a certain type of reactor is called a sodium fast reactor. The photo on the top left there is the last fast reactor that we had in the United States, the fast flux test facility. But what makes these problems interesting is the structure of the fuel. In the lower left there, that's our nuclear fuel, and we bond a helical wrap around the outside to promote turbulent flow and mixing within the fuel. Companies that are pursuing technologies like this use fast-running methods. They're called subchannel methods. It's a form of finite volume method specific for nuclear engineering. But they have a lot of constitutive models in them. And so we look at CFD calculations of these very detailed geometries to extract and post-process information that feed into and inform fast-running methods used in industry. We also look at quantities related to safety. This simulation here in the bottom right represents a flow blockage scenario. If there's some part in your plant that breaks free, makes its way into the core, and somehow lodges itself in your fuel, that's going to block the coolant from removing that fission heat. That will cause temperatures to go up, and you would like to understand, is something going to fail when that happens? And so this is a large eddy simulation with NEC-RS showing this type of calculation, from which you can understand how well would a sub-channel code predict the same thing. Okay, the last example I'll show you, this third category of how HPC is used for nuclear, has to do with whole device behavior. As I already mentioned with pebble bed reactors, we can't always break down a nuclear reactor into a unit cell or something small. We'd miss something about the boundary conditions we're trying to apply to that. So some reactors we have to represent as whole device. A good example of this is a fusion device. Here is a model of the JET tokamak from UK AEA, looking at the neutron flux spectrum in the entire facility. This is a very large scale here. I think you can see from those numbers there the scale of this, but this is meters and meters, meters by meters size. And it's important to know the neutron flux because from that you can learn the dose to people, you can learn activation of components, and many other important quantities. So these types of calculations really allow us to look at how small gaps and how we put together shielding materials could allow radiation to sneak through, and how to design around that. Another example of full system behavior would be a molten salt fast reactor. This is one of those types of reactors which has never existed before. What makes these reactors very interesting is that they use a liquid fuel. So rather than our conventional solid uranium fuel pellets or triso particles, our fuel is molten and flowing inside of a large open cavity. So there's a lot of fundamental physics we want to still explore about these systems. How does the turbulent structures and the temperature changes to the density influence the feedback to the neutron transport? But we can start to look at these systems now using HPC at scale. Okay, I promised I would talk about why performance is not everything for nuclear, so here it is. We are perhaps the most regulated field of engineering that you can find. Every aspect of design, operations, and maintenance that touches safety, that has a safety consequence, is subject to regulatory approval. And so whenever software and simulation is used to support design of safety significant components, which includes the reactor, of course, we care a lot about quality assurance of that software. And this isn't necessarily a sexy topic, but it's a very important topic for us. There's a lot of community consensus standards from ASME or IEEE on quality assurance for software. We look a lot at the Nuclear Quality Assurance 1 standard from ASME. And so this HPC performance software follows a lot of the standards in there for traceability of code requirements to tests, to documentation, and V&V, and a lot more. I want to note that HPC also serves a really important role in large-scale code testing. If we use these very high-fidelity calculations to support nuclear design, that should be part of a test suite that we are running for that code weekly or monthly on some kind of convenient frequency. And so for instance, for the tools shown today, we use systems at Idaho National Laboratory as part of their HPC center that are dedicated just to code testing. And this helps us ensure that we meet these quality assurance standards. In nuclear, public-private partnerships have played a really big role in connecting the capabilities of the National Lab supercomputers with stakeholders. So programs such as GAIN or Infuse are really important to getting these results in the hands of industry. Okay, I'm at the second part of my talk now. And that part is looking at this duality of nuclear, how nuclear can be this complementary technology to data centers. And Ben gave a really nice overview of this surge we're seeing in this energy demand. Can nuclear provide some of that? I think so. So I want to show you some trends that I'm looking at in nuclear that are trying to grow to meet that demand. In the United States, most licenses for power plants were initially granted to be 40 years long, mostly based on economic considerations, not necessarily technical. Most of the plants in the United States have gotten lifetime extensions of 60 years, and more are going for 80 years. So this is important work that the Nuclear Regulatory Commission is supporting and making sure that our current fleet of nuclear reactors continues to be available to provide power. Over the last 4 decades, we've added, on average to the grid, about 200 megawatts per year, just from power uprates. So that means we have a power plant, but maybe we can purchase more advanced instrumentation, a more powerful pump, a more powerful turbine, to allow us to boost that power by a couple percent. There's a lot of this still on the grid that can be unlocked. There remains another couple gigawatts of power uprates that we can go for. Very exciting to me is that there are 3 active projects in the US right now related to restarting nuclear reactors that had previously been in decommissioning status. One of those, Palisades in Michigan, has successfully reemerged from decommissioning to operations. They're not yet producing electricity, but I think this is a wonderful testament to the flexibility of the regulator and the industry to support this important return of generation to the grid. Now, this is probably also limited. There's been 10 plants or so that have shut down in the last 10 years. Those would be the best candidates to look at, but I do think it's important to note and very exciting. There are reactor demonstration projects going on all around the country. Without singling any of them out, these are occurring through DOE programs like the Advanced Reactor Demonstration Program and utilizing a lot of the infrastructure at the national laboratories as test beds. I will mention one that is particularly near and dear to me in that a couple universities are trying to bring microreactors to their campus. So University of Illinois is one of those. We're partnering with a helium high-temperature gas reactor vendor to build a microreactor on our campus to really provide that instructional facility for students and to be an at-scale demonstration. This won't be a typical research reactor for irradiating materials. It'll be something that looks prototypic of where we see the industry going. A big challenge for nuclear, I think, will be on the supply chain side. A lot of these reactors rely on high enrichment fuels. They rely on reactor pressure vessels, things that are produced to quality assurance standards for nuclear, and there may not be a lot of that out there. So what will be important is seeing a consistent, sure demand for that on the consumer side, so that suppliers of that have confidence to build out that capacity in those factories to create that. As an educator, of course, I look at workforce development very closely. If nuclear is going to be scaled the way that we are projecting, we're going to need a lot of investment on the workforce. And that has to predate that. It can't be something that we wait until it's too late. And that needs to happen across all levels of education and outside nuclear. Community colleges, technicians, bachelor's, master's, PhD are all necessary. At the University of Illinois, we've broken records the last couple of years for the number of bachelor students we are admitting to our program. So the current generation of engineers is very excited to start on this topic. So I'll close with one slide about one research question we are looking at in partnership with Idaho National Laboratory about how nuclear could provide energy to data centers. So if you look at a typical HPC system and you look at the load of these systems, there's large changes in that load, up to 30% per minute. For technical reasons, we typically don't design nuclear reactors to follow that load. They're usually limited to 10% per minute or a lot less, if at all. So one question we want to understand is, how could a nuclear reactor be a direct power provider to a microgrid, perhaps with an HPC load on it? And so we can look at things like intrinsic timescales in the nuclear reactor related to moving control systems, changing chemical shim, and how that might influence its integration into a microgrid. The University of Illinois campus is a microgrid, and this is a really perfect demonstration of this. But in this project, we'll be testing ideas for autonomous control of reactors and how that influences power quality with a real nuclear reactor. The Purdue 1 reactor, there's a photo of it down there. This is a research reactor, but we'll be connecting a surrogate model of an HPC load to a control rod drive in this reactor to see how changes to neutron populations and output might be tailored well with an HPC load. So I'll close here with my theory that HPC will be a driving force in delivering advanced fusion and fission power to the grid. Revolutions in technology require revolutions in energy. I think nuclear is ready to meet that moment. We're seeing a lot of use of HPC to design internally, to improve our nuclear designs, to meet very diverse energy markets, to provide that power for this growth in energy that we're seeing, not only at data centers, but just around the world. So I'll close here, and thank you so much for your time. It's been wonderful being here. I'll take any questions if there are any. So thank you.
Thank you, April. If we have questions, if you can come up to the microphone. And I do have a question. Oops, I just lost it up here. That's on, there it is. Sorry, I had it up and I lost it. So,
we have some in the audience if you want to pull
okay,
that up. Wow.
why don't we go with the audience? Thank you for
Hi.
looking for me.
I wanted to ask, what do you think the deployment or the timeline of the deployment for SMRs are? And also, how connected do you think AI and SMRs are? So let's say the AI is a bubble and the profits aren't as big as we think they're going to be. Do you think there's over, I think, 20 different reactor designs in the US, which is a lot? Do you think we'll ever standardize? Or do you think we'll see SMR developers kind of disintegrate and there'll be less and less, especially if the AI demand isn't as big as we think?
This is a great question. You're right, there's 20, I would say maybe 30, 40, if you talk about fission alone, and then if you talk about fusion, add another 40 on top of that. So there is huge diversity right now in the startups that are trying to commercialize these technologies. I think there will have to be some amount of consolidation. Right now, I think it's too early to predict what that steady number is going to be, if it's going to be 10 or 5. But I think it will certainly be more than just 2, which is more or less what we have in the United States right now. I think what we will see for sure is a variety in sizes. So right now, we have gigawatt-scale power plants. That's the vast majority in the US. SMRs, those are around 300 megawatts. But there's also a lot of companies pursuing microreactors, which are 20 megawatts or less. And so if you think about those very different markets, microreactors could see a lot of deployment, I think, for remote communities, mining sites, industrial sites that are tailored to a specific single customer. I think SMRs we may see for more baseload generation as well, but maybe in grids that don't need a whole gigawatt to be added at once. But I think there will be some consolidation. And I think I talked about data centers a lot. I hope it's not hinging only on that for nuclear to be successful, because we, of course, still want to decarbonize the grid that we have. And nuclear is a good baseload solution to that. If you add things like renewable, you're basically counting on adding more gas as backup generation for when those are not available.
What do you think the timeline is for that, though?
Yes, so there are a number of reactor projects under construction in the United States right now. For instance, the TerraPower Natrium plant is under construction in Wyoming. Plants are under construction in Tennessee. Prototypes, first of kind prototypes.
And one in Canada, I believe, the first demo SMR.
Yes, likely, yeah. So I think, those have time horizons of a couple years, I think, until they're fully ready and connected to the grid.
Okay, and by a couple years, you mean early 30s?
Early 2030s, I would say.
Okay, all right, thank you.
Thanks. There are representatives from these companies who are here in the audience, so I'm sure they have more concrete numbers.
Okay.
Hi, thank you for the talk. So my question is, while using SMRs or nuclear reactors for powering data centers, do you think poison effects like xenon would cause problems and require some off time of the nuclear reactor? The reactor cannot produce power at that time, so we'd have to have other alternate power supply during that time. How often can this happen? And or do you think, you mentioned the molten salt reactors, I think they don't have that much xenon problems because I think they are gas as opposed to liquid fuel, and they can isolate the gas away. So do you think SMRs would be made using such technology so that they can avoid the xenon problems, or can you comment on that?
Thank you for the question. I get to talk about nuclear physics. Excellent. So xenon is a fission product. Decays from iodine, which is a fission product. You may hear about things like xenon poison. So when you shut down a reactor, whether it's for something routine or for maintenance, that xenon builds up on a time scale of a couple hours. That xenon likes to consume neutrons. It has the highest probability of doing that, xenon-135, of any isotope on the chart of the nuclides. So that builds up over time, meaning that you can't turn your reactor back on, no matter how hard you want it to, until it's decayed back down. That can be 12, 24 hours. So that only happens if you change the power of your reactor. So if you run your reactor at steady state, this is not an issue for you. You have a steady state amount of xenon, and so you can continue operating in steady state. This is exactly the reason why it's very hard to load follow a reactor. That said, xenon likes to consume what we call thermal neutrons, slow neutrons. So some reactor technologies don't have very many neutrons in that range. And so xenon poisoning is less of an operational issue. So if you were going to load follow something, I would suggest it would be something that's a fast spectrum reactor if your main concern is related to xenon.
Right. Like you mentioned that data centers would require 30% per minute ramp rate. So, so we can't possibly follow, like the SMRs can't possibly load follow that fast without facing such xenon problems, right?
Yeah, thank you for the question. So the idea of the research that I talked about in the very last slide of what we're hoping to explore of nuclear providing energy to something that does have big variations in load is that you would rely on additional backup power, like from the grid. Maybe you decide to pull extra power from the grid when you go above your availability from the reactor, or you dump power from the reactor to the grid if you're below that. So it needs to be a hybrid system where you have storage and generation working together in concert. But the idea is that we would operate the reactor at steady state.
Okay, thank you.
Thank you.
All right, well, I'd like to have us all thank April again for her exciting talk in the future. Thank you.
Thank you. Thanks.
And that concludes our session for today, and hope you have a good rest of the week.